This film gives the different players within the building industry a basic understanding of the differences and similarities in the way we used to build and the way we will build all over Europe in the future. 40% of all the energy we use in Europe is spent on heating or cooling our buildings. This is 40% we can easily eliminate right away. We don't need to invent the wheel, that's already been done. We just need to develop it. An energy budget for this kind of house is between €0 and €400. Impressive, quite frankly. Someone took the lead and proved that this is not just theory, it can be done in practice. Now, the houses are here. It's possible to build a house with an extremely low consumption of energy using well-known building traditions. This is documented by the 10 passive houses built by isover in Denmark in 2008-2009. The houses are structurally quite different, but no matter if you build a light or a heavyweight construction, you can be energy efficient. But what's it take? First of all, good insulation, no thermal bridges, an airtight envelope, energy-efficient windows, and ventilation with heat recovery. The house retains the heat, so to speak. It uses the heat from the sun and the heat generated by the occupants and their electrical appliances. From the roof down to the foundation, a fully insulated, airtight envelope guarantees heat insulation. Fresh air intake and heat distribution are managed via a ventilation system with heat recovery. Just like a thermos, the better you retain the heat, the less energy you need to generate new heat. This thermography shows that a coffee maker takes a lot of energy to keep the coffee hot, unlike the thermos. The house has to be built tightly sealed, almost as if it were a large thermos. This makes demands on some of the building materials and calls for a painstaking effort to avoid thermal bridges and envelope leaks. But the construction methods are basically the same ones we're accustomed to using. The foundation's extremely important. We need a very low linear transmission loss. For this house, 380 millimeters of insulation was chosen for the cavity between the inner and outer leaf. Inside the house, 550 millimeters of insulation is installed in the floor itself. By placing the floor insulation 100 millimeters below the foundation insulation, your blinding concrete will go down to the inner leaf element when it's cast, making a fixed connection from the inner wall down into the foundation. This provides a strong insulation layer all the way out to the foundation. Let's see what this foundation looks like in the design. A foundation of lightweight concrete blocks is built on top of a base of lightweight concrete beads. The cavity is insulated with 380 millimeters of glass wool. The slap-on ground is insulated with a total of 550 millimeters of polystyrene, topped by 100 millimeters of concrete cast in situ.
Angående fundamenter på det her hus her, der har vi valgt en løsning.
A double leaf foundation, internal and external, with insulation in between, is used for this house. This design minimizes the thermal bridge. There's no other way to achieve the U values of this foundation. This gives us a zone where the insulation is placed and where the load-bearing elements, being plywood rafters, for the main structural elements of the house can be installed. The foundation of this house is not load-bearing. Seen from the outside, it consists of 150 millimeters of lightweight concrete blocks, 80 millimeters of polystyrene, 100 millimeters of lightweight concrete blocks, and another 100 millimeters of polystyrene. A radon and moisture barrier is placed over the slap-on ground, which consists of 440 millimeters of polystyrene with a concrete layer. The foundation chosen for this house is made of standard thermo blocks. This is not enough for a passive house, which requires a lower linear transmission loss. This house is constructed with external facade insulation, where gypsum is applied directly to an insulation material suitable for the purpose. In addition, the facade insulation extends right down to the ground, thereby providing an unbroken layer of insulation from the facade into the ground. This way, the whole foundation is also insulated. As opposed to a traditional wooden house, we use a through-going I-beam construction. This gives us a very high wood percentage in our external walls. As we wanted to reduce the wood percentage to obtain a better U value for the walls, we came up with this solution, where we place a batten at the back edge and a batten at the front edge. We then connect the two battens using two thin plates and fill up with glass wool in between. This approach has enabled me to reduce wood percentage to 3% from 7.5% for a normal wood frame construction. This makes it easier to obtain the U values stated in the energy frame calculations made by the engineers. If I'm required to add 10 centimeters of insulation in the wall, we'll simply cut the plate 10 centimeters wider and fill in with more insulation. In this way, I'll still have a low wood percentage, but a thicker wall. The external walls on this house consist of 290 millimeters of insulation clad on the outside with 15 millimeters of vapor-permeable fiber gypsum, topped by an additional 120 millimeters of facade insulation and a 10 millimeter rendering. Internally, a climate membrane has been fitted together with 45 by 45 battens and with a filling of 45 millimeter insulation. The finish consists of 2 times 12.5 meter fiber gypsum. Today, it's extremely important to make a tight building structure. We must make a blower door test, that is a pressure test, on the house. And if we don't carefully install the vapor barrier, corner solutions, solutions at the sill and solutions at the roof, the house will fail the blower door test. In the old days, the vapor barrier was placed here, right between the plates. This meant that every time the electrician or plumber drilled a hole in the wall, he punctured the vapor barrier, which obviously we weren't too happy about. That's why modern vapor barriers are placed 45 millimeters to the inside, meaning that you have an extra layer, 45 millimeters, followed by the plate out here. This means the electrician can route all his conduits through this insulation duct without breaking the vapor barrier. A vapor barrier or intelligent climate membrane is used wherever there are joints, and a line of butyl is applied. Afterwards, the joint is squeezed together, so we have a joint that's both glued and squeezed together. It doesn't get any better than this. Here at the windows, the climate membrane goes all the way out. As a result, the window's placed out here. This makes it possible to make a good seal between the climate membrane and the window. Ducts and lead-ins through the building envelope are always the points where leaks occur. But when we do it this way, we lay the groundwork for establishing a sound, tight solution. Today, a whole range of products are on the market, such as sealing strips and joint strips, so the problems can certainly be solved. You only need to think carefully from day one, before you start building. The main concept with this house is to build a standard single-family house that we can sell again elsewhere. Also, we wanted the external wall structure to be as thin as possible, with as much unbroken insulation as possible. The main structure consists of plywood rafters, delivered in whole elements with columns and beams covering the full width of the house, in this case more than 10 meters. The plywood rafters are spaced at 1.22 meter intervals, a modular dimension that matches the plywood plates. Plywood is fitted on the outside of the plywood rafters as a facade structure and as plywood rafter supports. 300 millimeters of glass wool are installed between the plywood rafters in this house. The external cladding is plywood and 80 millimeters of facade insulation topped by a rendering layer. On the inside of the insulation is a climate membrane followed by 45 millimeters of insulated lath layer. Plywood and gypsum plates sit on the lath layer. Let's compare this to an ordinary house, which on the inside has a load-bearing concrete or brick wall, insulation and a brick wall on the outside. Since the inside wall bears the load of the roof, the outside facade is actually just wallpaper, you might say. That's how things have developed in the industry. We've chosen to leave out the brick facade and use plaster on the house instead.
På indersiden der bliver der monteret 45 mm forskalling.
On the side, we fit a lath layer of 45 millimeters. This concept allows us to lead in cables and wall outlets without breaking the vapor barrier. And this is important for keeping the house completely airtight. We believe we've obtained a flexible structure. Over time, a house like this will develop. Perhaps the walls will be moved or partition walls torn down and replaced by new ones without interfering with the vapor barrier. In low-energy houses and passive houses, the installation of a climate membrane is particularly important. The membrane is a must for obtaining the air tightness required to make the house retain the heat and obtain controlled ventilation and intake of fresh air through the ventilation system. The climate membrane is placed on the warm side of the insulation, in other words, the side facing the room. There must be a 10 centimeter overlap between the strips of membrane. Good, durable adhesive tape must be used to seal them. Staples do not provide airtight sealing of membrane strips. In this house, the climate membrane covers all rooms to avoid many of the difficult joints at the walls. A sealant must be applied wherever the membrane adjoins a solid structural component. Obtaining air tightness between a heavy inner leaf and the vapor barrier at the ceiling requires preparation. We've done so here by inserting a sealing strip on top of the outer leaf. We then laid the wall plate up here, put the rafters on top of this, and placed a vapor barrier in between. The barriers cut off in strips of about 75 centimeters and wedged in here. When the vapor barrier comes from the ceiling, we apply adhesive tape. This gives us complete air tightness between the heavy outer leaf and the vapor barrier in the ceiling. The insulation must be entirely level to ensure good insulation of the ceiling and completely devoid of holes or cracks where cold air could penetrate. It's important to cut the insulation so it tightly adjoins the ties. When you insulate a roof structure, complete air tightness must be obtained so that no air will reach the insulation from the outside. Here, this has been obtained by taking the outer leaf all the way up between the rafters, followed by a joint along the rafters and the outer leaf and the fitting of a plywood wind cassette. A joint's been applied all the way around to make the structure completely airtight. The roof cassettes for this project were made for a hot roof, so there's no traditional vapor barrier at the bottom of the cassettes. On top, where the plywood's located, is a layer of roofing felt that acts as a vapor barrier. This is followed by a layer of insulation and another layer of roofing felt. The ratio between the insulation in the cassette and the insulation for the roof can be subjected to a moisture technology calculation. The result could be 50 centimeters. And this gives some problems up there. The climate membrane stops at the upper edge of the wall. Then I have a 20 centimeter high roof cassette and my vapor barriers up there too. This means I have a 20 centimeter joint without any real vapor barrier. So we solved this by gluing all the joints. All the end boards have been glued between the plywood and the bottom plate. And this should keep it tight. There are special challenges when installing a window in a passive house because the insulation is so thick. Here we have 380 millimeters of insulation, so there is a cavity of 380 millimeters. There's really nothing to which the window can be attached. That's why we fit composite material plates around the window casement. These plates have a very low lambda value, so their insulating capacity is almost as good as the glass wool in the wall cavity. The composite material plate is fitted with ceiling strips directly onto the window casement before the window is installed. The window casement goes back so far that it covers the outer leaf. It's then fitted through the composite material plate into the outer leaf and reinforced because of the very large window using brackets of the exact same material. These energy-efficient windows have very thick casements. To make them look slimmer, we let the brickwork cover some of the casement to establish a joint between the aluminium edge, which makes the window maintenance-free, and the casement, and this gives a nice closing section. This house is made in the form of a wooden prefab house. The wooden element extends to where the vapor barrier comes up. The wooden battens and the gypsum plate form the insulation layer, through which electric cables can be inserted. Sealing against the window is ensured by leading the vapor barrier up and across the bottom piece here. The window has been pre-fitted with a piece of vapor barrier material. Two vapor barriers are glued and joined very carefully to guarantee the required air tightness. This is a brick house that also has bricks in the outer leaf. Here, the window detail has been made by attaching the window to the outer leaf with a strong fitting. Air tightness has been ensured by this airtight cloth fitted to the window before it's installed. The cloth is pulled out here, and an airtight membrane is fitted to the outer leaf with a joint and adhesive tape, followed by a sealing strip. When you make these routing ducts for injecting and extracting air, it's important not to place them directly in the ceiling, as is done in many other houses, but to place them as far down in the house as possible. The best solution is to place the duct